This is 9.2 in Chapter 9 of your physics book. We're going to talk about the applications of gravity. So we spent 9.1 talking about the universal law of gravitation and the formula. And so now we're going to look at how this applies to different situations that we come in contact with. So Newton used this law of gravitation to explain and applied it to a lot of very interesting situations. And one of them was that the force exerted by a spherical mass. Okay. So he used this is like I've been telling y'all before, this is where everything we've learned in math gets applied to a problem. And Newton did the same thing. He used calculus. And by using calculus, he was able to prove that a spherical mass exerts the same gravitational force on masses outside of it as it would if all the masses were located at its center. Okay, so whether something's on the surface of the Earth or whether something's at the center, there's not a big difference in the gravitational force of that situation. Okay, so so here's just a figure describing that same thing. And like I said, he gets into calculus, and we're not going to get into that calculus. Just understand from this diagram that whether you're looking at a sphere or just a little point, the force of attraction between those two things is going to be the same as if they were both just point masses. Okay, so that's the main thing to get out of that. There's nothing really more complicated than that, unless you want to do the calculus for that. And that's another class. All right. Since the Earth is approximately spherical, the results can be used to determine the force exerted on an object on the surface of the Earth. So again, it doesn't matter if you're on the surface or on the center. You're going to use the same formula. Your radiuses and your masses will be different, obviously. So the radius is going to be the radius of the Earth. So if you have, here's the Earth, you have an object near the Earth, then the force of attraction between the object and that Earth and the Earth is going to be equal to whatever the mass of that object is, the mass of the Earth times the radius of the Earth. Okay, you'll plug that into your universal law of gravitation, and that'll help you define the magnitude of that force. So we can use that equation if we remember that gravitational force experienced by a mass on the Earth's surface is also given by mass times acceleration due to gravity, and we set those two things equal each other, we can use that to calculate and solve for what g is. So we know g is 9.81 meters per second squared. How do we know that? Because we plugged in the constant for g, the mass of the Earth, the radius of the Earth. We plugged into that formula and solved for g. Okay? And that's acceleration due to gravity. Now, this g is assuming that the Earth is perfectly spherical and has a uniform distribution. We know that's not true. We also know that the calculated value for g changes depending on where you are. If you're on top of Mount Everest, you're going to have a different value for g, a smaller value for g, compared to if you are in New Orleans, which is below sea level. Okay. Now, the value is not going to be hugely different, but it will be different. And that's because the Earth's not perfectly spherical. You do have some changes, some deviations in its shape and structure. Okay. But for the most part, it is going to be 9.8 meters per second, unless they tell you otherwise. Okay. So this graph is just a graph of the gravity. It's called the gravity map. And it's constructed by satellites they take different combinations of surfaces and their gravity measurements and satellite tracking data and all that. And they come up with places that have the strongest gravitational pull and places that have the weakest gravitational pull. So the blue areas are your weakest gravitational pull, the red areas are your strongest. The point of gravitational maps, or why do we have a map that measures out the different where gravity is strongest and weakest, is it helps us get information on ocean currents, on seismic activity, and very importantly, petroleum deposits, where we find oil. So all of those factor can be we can use a gravity map to help give us that information. All right. So gravity on other astronomical bodies like the moon or Jupiter or Mars or different planets, whatever, can be found by just tweaking that same formula that we use to find it on Earth. Rather than having mass of the Earth and radius of the Earth, we're still going to have those three things: the gravitational constant, the mass of whatever object that happens to be, and the radius of that particular object. And with those three things, we can find the acceleration due to gravity on any surface, on any object. So we know the acceleration due to gravity on the surface of the moon. We could find the gravitational acceleration due to gravity on the surface of Mars or wherever, if we know the mass and the radius. Okay. All right. So a man named Henry Cavendish, again, applied this information that Newton found, and he used it to find the value of G, the actual value of G that we now use, and also to help us find the mass of the Earth. Okay, so here's an example of finding G on the moon. If we know the moon's mass and we know the moon's radius, all we need to do is plug into this formula and we'll get acceleration due to gravity on the surface of the moon. It's 1.62 meters per second squared. And that should make sense since we know that gravity is about 1/6 that on Earth. If the Earth is 9.8, then it kind of makes sense that the moon would be about 1.6. So in 1978, Henry Cavendish measured the value of G that appears in the universal gravitational formula, and found that G was an extremely small number. That's why it took over 100 years to find out what that number was, because it's so small. Whoops. All right, so the experiment that he used is pretty interesting. So this is the Cavendish experiment. And what he did is he had two large masses that you see here and here. And then he had a thread attached to a bar with two other smaller masses attached to it. And he suspended that bar from this thread and just observed what happened. Okay. So when he suspended it, each suspended mass was near a larger mass. What he would then do, the gravitational attraction between the masses causes the rod to twist. So what he noticed is if he suspended it, that this rod began to twist in this direction, that the smaller masses moved toward the larger masses. And that twist angle is what he used to measure the force, the gravitational force. Okay. So in essence, sometimes we say that Cavendish weighed the Earth because once he knew what G was, then you could plug back into these other formulas and rearrange them to find the mass of the Earth itself. Because obviously we can't go put it on a balance. So the way we take the mass of something when we can't just go sit it on a balance is we have to use math. Okay, so we knew what G was, little g. We know what capital G is. So then we can rearrange this equation and solve for the mass of the Earth, and that's just what Cavendish did. and calculated what the mass of the Earth should be. Okay, so like I was saying, this is where the concepts and things that you learn in math, I was telling you all this the other day, the concepts and things that you learn in math apply in our everyday life. And science is where we use all that information and it becomes something that we can discover, something that we can use in other applications. It's not just a number. It's not just a calculation for a calculation's sake. So he just used algebra and calculus to rearrange this equation and solve for mass of the Earth. Okay, so sometimes life is just one big word problem. All right. Oops. There we go. So the following example shows how the knowledge of G and quantities of little g and r were used to determine the mass of the Earth. Okay, so again, we just plugged those values in. We knew what little g is, 9.8. We know the radius of the Earth because we know the circumference of the Earth. So again, we can use algebra. If we know the circumference of the Earth, we can work backwards and find the radius of the Earth. We don't have to literally go to the center and measure out. We use math. Okay, because remember, circumference is 2 pi r. So we know the distance all the way around the Earth, so then we can very easily rearrange and find the radius. And then we had found this constant capital G, and so we can plug all that in and find that the mass of the Earth is 5.97 times 10 to the 24th kilograms. And we don't need a balance that big to put it on. Okay. So, why is that important? Why do we need to know the mass of the Earth? Well, one of the things it does is if we know the mass of the Earth, then we can find the density, the average density of the Earth. So typical rocks near the surface of the Earth tend to have a density of about 3 grams per cubic centimeter, and the density of the Earth itself is 5.5 grams per cubic centimeter. So the interior of the Earth must have a density that's greater than that of its surface. And we've confirmed that with seismic wave analysis. So when we have an earthquake and we measure this seismic activity, that can be used to help us determine or confirm that the density of the inner core of the Earth is about 15 grams per cubic centimeter. Again, we don't want to go to the inner core of the Earth and have to take that measurement by hand. So we use math and we use technology and instrumentation, and we can calculate what the density of the inner core of the Earth is. So let's talk a little bit about Einstein's theory of relativity. Remember, the basic formula for that is E equals mc squared. So according to the theory of general relativity, the gravity of a large star, so the bigger the mass of something, the more energy it has. So it is theorized that as a star becomes bigger and bigger and bigger and bigger, it can get so big that nothing can escape it. And by escape it, I mean it has a gravitational attraction for everything, and that gravitational attraction can't be overcome. So nothing can escape, even light. And that's what we know as a black hole. So you don't hear a lot about them all the time, but that's what a black hole is. It's a star that has become so big with so much gravitational attractive force that nothing is able to escape out of the gravitational pull of that object. And so it's called a black hole because not even light can get out. And that's just shown in the figure there on the side. So with all of this indirect evidence meaning Newton's law of gravitation, we pair that with Einstein's theory of general relativity, we pair that with being able to calculate or having calculated G, capital G and lowercase g, and all of those other things, we get indirect evidence for the existence of a black hole. And that's all we're going to talk about, black holes. So, well, we'll talk about it a little bit more. Einstein's theory of relativity also predicts that any amount of mass can bend light. Light is energy. And so any amount of mass that something has can cause that energy, that light energy, to bend. When that happens, sometimes if we take a picture of something that's a long way away, like a distant galaxy or whatever, you get lots of images on the photograph instead of just one. Even though you know there's just one thing there, you get lots of different images. So you can see this as an example. Here's our distant object. These are the images that you see from the Earth. So instead of seeing one, you might see multiples of them. And that's because of Einstein's theory of relativity, that even any objects can bend light. This causes the light being bent by galaxies or black holes. And so this effect is known as gravitational lensing. So that's where we get an idea of where a particular galaxy might be or how far away it might be, is because of how it bends the light. And we'll talk about the other things later on, but okay. And that is it for 9.2.